We'll be talking about fluctuations or shocks in the asymmetric simple exclusion process. Welcome, Patrik. Over to you. Thank you.
Thank you for inviting me to give the talk. I opted for a long time to come, and in the end, I did not come in person, but it is as it is. I will speak about fluctuation around shock and of the shock in the totally asymmetric simple exclusion process. So first, I will introduce some basic, and then I will give a couple of results. And the basic are useful to understand why the results are true. It is why I'm introducing. Some stuff I can do a bit faster than in typical talk because everyone knows the exclusion process. So the particle, just to fix the notation, that eta j will be the particle occupation at position j, and my particle jump to the right with rate 1. And looking at total asymmetric, and exactly like in Jeremy's talk, I use the ordering right to left for the particle. Here, one can associate, of course, an height function is exactly upside down with respect to the notation of Jeremy. The important point here is that you set up the height function at 0 at some position, and then the discrete gradient is given in terms of whether there is a particle or not. So if the discrete gradient 1 minus 2 times the occupation of this side. Now, one important stuff is first to understand the picture macroscopically, because shock will appear when something macroscopically happens. So if you think, if you have some height function and you do the hydrodynamic scaling that everyone in this audience should know, given the title of the conference, you have an HMA is the macroscopic limit shape that is, in this case, for KPZ models like TASEP or other, will be non-random. And the macroscopic density, rho, is just the linear transformation of the gradient here. Just because I choose this one, this is the gradient, and 1 minus 2 times the density. So everyone knows here that for TASEP, rho solves the Burgers equation. It's this evolution. And then here is what happens. So suppose that you have initially a density rho minus a particle. Here we are looking at the Burgers equation, and then to the right of 0, density rho plus. Then this discontinuity in the density will remain, is not disappearing, and will move to the left or right, depending on 1 minus rho minus rho plus. This will be the speed of the shock. So this will, macroscopically, this is something that well deterministic. This discontinuity that remains in time is called a shock. So we will try to understand the fluctuation of particle in a neighborhood of a shock, as well as the fluctuation of the shock, or more precisely, the fluctuation of the second-class particle. Now, one important ingredient are the characteristic solution. So if I call U the macroscopic slope, then you can compute the speed of growth as a function of U, depending on the model. In TASEP, the speed of growth as a function of U turns out to be 1/2 1 minus U squared. Then you can write down a PDE for U. So this is the PDE for U, and this A is minus the derivative of speed of growth as a function of the slope. Now the characteristic solution are physically meaningful. The solution actually of the PDE, so that the slope is constant in time, and the speed of this line is given by A of U. So in our case of TASEP, A of U is U. So the characteristic line will have a speed U equal U, which means in terms of density of particle, 1 minus 2 rho. So if you start the characteristic line, if you have a density rho constant, then it will be just all a line with a slope speed 1 minus 2 rho. Now, what is a shock? A shock corresponds to the case where several characteristic solutions collide. So for example, when you have density rho minus here and rho plus here, then 1 minus 2 rho minus will be larger than 1 minus 2 rho plus, which means if you start from here, to start a characteristic solution from here and one from here, they eventually meet in this point. So when characteristic solution meets, this is the location of the shock. Why these characteristic lines are important? Because physically are the one where the correlation is non-trivial in space-time. So this is the goal of this slide. So consider, for example, the simplest case, the stationary case, Bernoulli with density rho as initial condition. You can define the two-point function which give you the correlation of the occupation variable at time t at position j and the occupation variable at time 0 at position 0. Now, the second class particle, it is a particle that moves as usual, but if a normal particle want to put on common this position, it has to give place and they exchange. So if you take C of t to be a second class particle starting from 0, then for this stationary initial condition, there is an identity that related you the position of the second class particle, the distribution of the position of the second class particle with the two-point function. Up to a constant is the same function. It's just a normalization constant. So the second class particle you have to imagine that it's just a microscopic representative of the macroscopic shock. So for example, it was shown that there is a non-trivial scaling for the two-point function, and therefore also for the distribution of the second class particle for stationary initial condition starting from 0. So the non-trivial scaling is when j is of like 1 minus 2 rho, because this is the speed of the second class particle, which is also the speed of the characteristic. It is why there is a relation between the two. And then the fluctuation here are non-trivial over a region of order t to the power 2 over 3. So this, looking at this is just for stationary, but this gives you the idea that if you look in space-time, the correlation at time over a time span of order t will be relevant only in a neighborhood of a characteristic, if you follow back the characteristic, in a neighborhood of size t to the 2/3 of the characteristic where you are. Now, the last ingredient that I actually need, that if you look at the height function or the position of particles, think at the height function here. Now, if you look at the height function at some position, in this case, a position 1 minus 2 rho times t at time t, and you compare this height function with the height function on a point of the characteristic. The characteristic here starts from 0 and goes with speed 1 minus 2 rho. So if you look at a time which can be very far away, but mesoscopic, then the difference is at first order, the law of large number, the difference of the law of large number. But if you divide by t to the 1/3, which is actually the typical fluctuation of h, then you don't see any difference. So essentially 2 points, as soon as you take 2 points along the characteristic, then in order to see a non-trivial correlation, you have to really look macroscopically. The point should be macroscopically away. So at time which are, say, t, if, for example, 1/2 t, or a proportion, something proportional to t. If the difference is smaller, then at first order, you don't see any. The first result I want to mention are around fluctuation around the shock. And good with the time. So first is mention 2 results, which are the fluctuation away from the shock. So if you have step initial condition, which means all particles are to the left of 0 are occupied and to the right is empty. Then if you look in any point which correspond to look in the so-called rarefaction fan, where the solution of the Purker's equation has a non-constant density, decreasing density, then the fluctuation of the particle position at time t will fluctuate of order t to the 1/3, and the distribution is governed by the GUE Tracy-Widon distribution. And similarly, but differently, if you take any flat initial condition, what is important here, if you take some non-random initial condition, so that the density, macroscopic density is constant, not decreasing like in a rarefaction fan, then the distribution of the particle. Here I took 0 because it's translation invariant, essentially. The distribution still fluctuates on the same scale, but has a different law. It's the GOE Tracy-Williams distribution. Now this one, these are these nice, they have these nice densities, which nowadays you can even plot easily using mathematical because they implemented this universal distribution inside Mathematica. And this is the first result we obtained quite a long time ago with Peter Nejjar. The first result is about the fluctuation of particle in a neighborhood of the shock for non-random initial conditions. So if you take, this was the first one we had, constant density initially until here, until position minus beta t, then everything empty, and then another block of particles. If I would have only one block of particle, I would have this situation, what Johansson already proved. Now, if you solve the Burger's equation, you see that at time t, the density of particle, macroscopic, it does like that, as this thick black line is the same. So here there is still a shock of a given height, but macroscopic. And what we prove is that if you take a particle with an index such that you are in a neighborhood of the origin. So the index should be so that you are in a t to the power 1/3 neighborhood of the shock. Then the distribution function turns out to be a product of two Tracy-Williams distribution. And the parameter here, everything is known. For example, rho 1 and rho 2 are actually the density just to the left or just to the right of this point. Important here is just to remark that there is a product. Second result I want to mention is what happens, suppose that you have a condition with 3 density, constant density, but non-random. So these are put regularly with density rho 1 to the left of 0, from 0 to capital T with density rho 2, and afterwards with density rho 3. Now here, the first shock is 1, we'll have a trajectory, and the speed will be 1 minus rho 1 minus rho 2. The second shock has also speed 1 minus rho 2 minus rho 3. And since this is smaller than this one, eventually they will merge. And the merging time is easy to compute. Macroscopically, it will be around capital T over rho 3 minus rho 1. Now, in terms of space, the space-time picture is this one. So you have a density rho 1 here, density rho 2 inside here, and density rho 3. So here are the characteristic lines, the 3 different density. So there are some line L1, L2, L3. So we are looking now, so L1 corresponds essentially to the picture that we already seen before, except that we have flat initial condition. But what we are looking here is in this point, where 2 shocks merge. Here we are looking at T to the power, capital T to the power 1 over 3 neighborhood, both in all the direction, both in time, both in space direction. So we take time, which fluctuates of order T to the 1/3, and particle like T to the 1/3 away. And what we prove is that in this case is the triple shock or double shock, whatever you call, then the distribution function of particle in this neighborhood is given as a product of 3 distribution functions. And then if you take some limit, for example, when you take tau goes to plus infinity and you follow this line, for example, then you will see that one of these FGOE will disappear. And you go back to the product of 2 of them. So here I would like to explain the heuristic explanation why it is true. The idea goes back to a result that date of a work of Seppalainen was not written in this term, but it is a consequence of one identity that he derived. So the position of particle n at time t can be written as a minimum of 3 different initial conditions. And this initial density, then you just couple with a basic coupling. So this is the initial density, the problem we want to consider. X1 is this one, X2 is this, as this density, and X3 is one. Now here comes in the key property of the slow decorrelation. The slow decorrelation in terms of particle, I'll keep here, would tell me that the position of particle n in the with initial condition L at time t. So of course you choose them so that they are all more or less at the same point, because you take a minimum. So if one is very much larger, essentially you don't see them. So you take the scaling so that macroscopically we actually all the three initial conditions correspond to, so that the particle will really arrive here. So the slow rate correlation tells me that for each of these initial conditions, the position of the particle n at time t is very well approximated the position of another on a particle with a different index at a time which is quite far away from the final time. So remember that capital small t, you can think that is equal is this one. Essentially is capital T over 3 minus 1. T is of order capital T, and then you go away, say, of order T to the 3/4, for example, something more than 2/3. This law of correlation tells me that this random variable is essentially equal to this up to smaller order, which disappear in the scaling because we have to divide by T to the 1/3 in the end. The second is the localization. Now, suppose that you can do this approximation, and what turns out, I told you something about the space-time correlation, that space-time correlation live on an order T to the 2/3 around the characteristic. So if you look at the characteristic that correspond to look at the position, the start from the position, what this typically is, for example, here, then the attend the, so if you think about the graphical construction of Tasset, there are trials of there are Poisson process or a Poisson process everywhere. So the only actually Poisson process which are relevant are the one actually in a T to the 2/3 neighborhood, this cylinder C1. And similarly for C2 and C3. But the point is that if you take nu more than 2/3, geometrically this cylinder don't intersect, which means asymptotically what you will have that this random variable with different L, this one, will be independent. And then if you center on scale, see, you divide by minus T to the 1/3, this minimum becomes a maximum. And now we have maximum of essentially independent random variable. Each one corresponds to have a flat initial condition. And therefore, since you have a maximum, in the rescaled version, you have the maximum of rescaled random variable. Then you have this product form. In the last 5 minutes, I want to mention something about the second class particle. So we start with a result of Pablo. This is Pablo, not me, and Fontes in 94. So in this paper, they prove much more than this result. Of course, this is just one of the results. So you take density rho minus, but Bernoulli is Bernoulli random variable to the left, and Bernoulli to the right is density rho plus. And Z of T is the position of second class particles starting from 0. Then they've proven that once you center in your scale by T to the 1/2, not like 1/3 like before, 1/2, the limiting result is a Gaussian. Actually, the point that the reason why I have 1/3 and here the Gaussian, this is actually coming from the initial condition, but not on the fact that the model is really Capizzi, as you might understand from later. Now, we try to look at what happened for non-random initial condition, but still with density rho minus on the left and rho plus to the right of 0. Then what we prove is that this distribution of the second class particle centered and divided by T to the 1/3 this time is given by the distribution is the difference of two independent GOE Tracy-Widon distributed random variables with some constant depending on the density. So suppose that a result like that is proven, but here with 1/2 and here we have Gaussian and Gaussian. Now the difference of the Gaussian will be a Gaussian. And this is actually why here you have a Gaussian. And this one is just coming, the Gaussian for this case is coming from the initial condition because we have random initial condition. Now, one way to understand this one, if you know what is the competition interface, if you don't, maybe it's too I don't have time to explain why, but if you have the competition interface, the initial condition with 2 density correspond to a start and last passage percolation from this line and then continue on this line. And if I put in a color the point where the last passage percolation from this line is greater than 1 from this line, and vice versa, the interface between the two was defined to be the competition interface. And for this one has the same trajectory, it's just a random time change, but the trajectory, if you look at a position and you project down, and this is considered to be the position, then you have the same trajectory as the second class particle. So if the second class particle do a jump to the right initially, and then 2 jump to the left and 1 to the right correspond to this situation. Now the distribution of the second class particle, now you can think that is more or less, it's not exactly, but it's similar to the distribution of the competition interface. So to know that the second class particle, say, is to the left of a given position, if you look at the projection, it corresponds that the LPP coming from this one minus the LPP coming from this one is positive. And since you have a difference of 2 LPP, and since we know that these two, by the slow correlation on all this stuff, are essentially asymptotically independent, this is the reason why you have a difference of 2 independent GUI. So actually the proof is a bit more complicated because except for the density, except when the speed of the second class particle is 0, there you have to be a bit more careful. But in principle is the reason. And just to conclude, I want to mention one more result about this fluctuation of the second class particle, where you consider a block of particle here with density 1, then a block of length BT, which is empty. Here you put a second class particle, and here you put all particle, and then empty. And this is length 80. If you look at the microscopic density at MT, that's of the Burger's equation, it turns out to have this form. So these two colors correspond to the light color correspond to this particle, and the darker color correspond to particles starting from here. This is the picture in terms of characteristic. And at some time, at the beginning, there is nothing, and then eventually particle to the left will come here and that will start to pile up and will create this jump. But initially there is also a shock, but it's a trivial because there is no particle to the left. We are interested when there is some interaction between the left and the right. And then using some multicolor TASEP developed by Borodin and Bufetov, one can, for this initial condition, write an explicit formula for the distribution of the second class particle in terms of the probability of the difference of two height functions. The important point is you look at function, you look here minus m plus and plus m minus, and these are all of order t, which means you look at the height function to position of the height function, which is very far away. So if it is very far away, they will be decorrelated. And this is the reason why under scaling, the limiting distribution of the second class particle is going to be a difference of two GUE Tracy-Widom distributed random variable, independent. The GUE come from the fact that because we are looking at here to the left and here, we are looking to rarefaction fan. If you would have the same like we made with Promit and Peter with flat, you have constant density and then you have GUE. With this is the last result I wanted to finish, since anyway the time is essentially over.
Okay, thank you very much. Let's thank Patrik. Yeah, maybe if there's one quick question. I don't see any on chat, but if there's a quick question.
Thank you, Patrik. Pablo here.
Yeah.
No, I was thinking maybe the difference for the current fluctuations or for the second class particle, the Gaussian fluctuations come from the initial condition, right?
Mm-hmm.
And what if you take the difference between the position of the second class particle and the initial conditions, the function of the initial conditions? This should give you a fluctuation of t to the 1/3, I guess. What do you think?
If you look at the difference, it should be on a smaller scale, because the reason why, as I mentioned, so if you would have the random, here you would have a random walk, and here you would have a random walk. And this random walk, since you will move away of order t, will get a bit Gaussian, so will be a Brownian motion essentially, and of order square root of t. But indeed, if you look with respect, the problem is that technically it's not easy to get a subleading fluctuation behavior with respect to a fluctuation behavior, but technically it should be smaller, yes. So the fluctuation which are the origin, the fluctuation which are actually the signature of the KPZ dynamics, KPZ type dynamics, should be on a smaller scale, like t to the 1/3. That is hard to get it directly, because you have to subtract, which is something which is larger and still fluctuating.
Thank you, Patrik.
Thank you very much. Let's thank Patrik again for a nice talk.